Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
And I'm pleased to welcome Maryam Fazel from UW, who will talk about optimization and sparse recovery.
Thank you. Oh, thanks. Is the microphone on? Everybody hears? Yeah? Okay. All right, so I'll be talking about recovery of simultaneously structured models using convex optimization. And this is joint work with my graduate student, Amin Jalali, who's here. There's Amin. And we have collaborators at Caltech, Professor Babak Hasibi and Samet Oymak, who's a graduate student at Caltech, as well as Yonina Eldar at Technion. So I'll also go ahead and introduce the rest of my group because they are also here. There's also Karthik Mohan, Dennis Meng, there's Dennis, Reza Ehwali, and Brian Hutchinson was here earlier. But OK, so I'm going to be talking about this general setup of we would like to fit a model to some given measurements or observations or information of that model. And we have some, you can think of it as prior information about the model. That is, this model is in some sense low dimensional. So you can think of this as actually kind of setting that Hari was talking about, for example. It could be low dimensional manifold in your data, or it could be other models. So I'm going to be talking about models with low dimensional structure. Also, you can think of it as low degrees of freedom relative to their ambient space. So they live in a high dimensional ambient space, but they have lower degrees of freedom than what the ambient would suggest. The goal is to recover such models given some kind of information or observation or measurements of these models. And the applications of this very broad idea come up in signal processing, in sensing and recovery of signals, various kinds of signals in machine learning, and in the topic of system identification in control, dynamical system identification. And the typical questions that come up, things we are interested in, are what kind of convex penalties or convex regularizer or regularizing functions can we construct to encourage our model to have the desired structure? And then how do we quantify the performance of such regularizers? So what do we mean by these low-dimensional structures or structured models? Some typical examples that have been studied recently a lot. Sparse vectors. So I have a vector in n dimensions where n is very large, but the vector has mostly zeros in it. And say it has k non-zero entries, and k is much less than n. And this particular object, its measurements and its recovery gave rise to the area of compressed sensing. It's a huge area by now. It also, the idea behind the lasso method by Tibshirani in '96, it's been used in a lot of application areas, in particular in image denoising. And another extension of that idea or another type of structure is group-sparse vectors. So vectors that also have a sparse structure, lots of zeros in them, but the zeros come in different groups. And there's group lasso, for example, that uses that idea. Another kind of structure, different kind, it's not about zeros or non-zeros anymore, is low-rank matrices. A matrix that has a small rank, a small number of non-zero singular values. And therefore, its range space and row and column space are low dimensional. So this low rank matrices come up in many areas as well. For example, collaborative filtering, an example of which is the movie recommendation system that, for example, Carlos mentioned this morning. Netflix, you want to recommend users to movies. A lot of methods for solving that problem are based on the low rank matrix model of the database matrix. So without going into detail, I'll just quickly mention some of these. So collaborative filtering, and it's been studied from this point of view by several people, also comes up in control of or identification of dynamical systems, system identification. Over there, you look for low-rank Hankel matrices. Another structure that came kind of sequentially after these is a model that is sparse plus low rank. So it's a matrix. It has a sparse component plus a low rank component. And that came up in, for example, robust principal component analysis, where the low rank component corresponds to the principal components, and the sparse component represents outliers, a sparse set of outliers that add to your or modify your principal component matrix. And also comes up in graphical models and so on. There's one more structure that is actually the focus of this talk. You can also have, not this kind, but you can have sparse and low rank appear differently. You can have a model that is simultaneously sparse and low rank. So for example, here I'm thinking of a matrix that has a lot of zero rows and columns in it, and also is low rank. So we will see much more about this and an application area of it later. So now the problem is this. Now that we saw what kind of structures we're talking about, recovery of these structures, the problem is usually set up like this. We have an unknown but structured model. Let's say we model it as a vector in Rn. Again, n is the ambient dimension, can be a large number. We are given observations of that model. So we have a linear map acting on that n-dimensional vector and giving us m measurements. So this is from Rn to Rm, where m is a lot less than n. So we have an underdetermined set of linear equations given on our unknown model. Now, the problem is this, or the goal is this. Given the measurement map, we can represent it by an m by n matrix as well in this simple case. And given the measurements, so there's m of those, and knowing the structure type, we want to find x naught, find the desired model. And a lot of recent research has focused on the following questions for different structures. One is, how do we find the desired model given these observations? It requires often setting up an optimization problem whose solution can be shown to be the desired model. And by the way, we want to find it in a computationally efficient way. And another question of a different kind, how many measurements m suffice? Or how large should m be for this to work? So recall m is the number of measurements, right? So it's in some sense a measure of the complexity of your model. How many measurements you need to recover? Of course, it depends on the type of measurement. So this question really doesn't mean anything if I just say it like that. But in order to quantify it and for the purpose of analysis, we are going to assume generic measurements, which means that I'm going to take this, the measurement map G, to be an m by n matrix whose entries are drawn from a Gaussian distribution, zero mean unit variance, standard normal. That makes that measurement matrix be representative of all m by n matrices in the sense of forming a dense open subset of all m by n matrices. And in that sense, it's generic. And it's typical assumption for this style of analysis. So what are existing results like this? You may have seen some of these. But the first one is, and the most famous, is recovery of sparse vectors. So I have x naught that is k-sparse, only k non-zeros. It lives in Rn. And I have m measurements of it. And one way I can try to recover that vector is that I can find the sparsest vector subject to my measurements. So this is L0 norm, which basically means the cardinality or the number of non-zero elements. If I could find among all x's that satisfy the measurements, the one that is the sparsest, then I can hope that I can recover the k-sparse one if I have enough measurements. So, but the problem is this is a non-convex problem and I can't really solve it. But as a benchmark, let's actually ask the question, how many measurements we need? How many m do we need for this to work? And to give us the unique solution to be x naught. And the answer here is, it's been studied before, and the answer is order of k. K is how many non-zeros is in the vector. And in some sense, that's the degrees of freedom, or the dimension of the low-dimensional manifold, if you want to think of it that way, that this particular structure the x lies on. So I need only order k observations for this program to give me the correct x naught. In fact, it's 2k plus 1 or something, but it's on the order of k. Now, this is not that useful of a result, but this one is extremely useful. I can't solve this because this cardinality function is not convex. However, if I relax it to this convex function, which is L1 norm of x, sum of absolute values of entries, now I can solve this problem because it's convex. And the same question has this answer. How many measurements do I need to recover x naught correctly? The number is on the order of k log n over k. So the important thing is it depends on k much more than it depends on n. In fact, the dependence on n is very minor, very mild. It's logarithmic. So if you look at these two results, it's striking that a convex relaxation needs on the same order modulo the log factor of measurements to recover the sparse vector. So when this result came out, it was actually a really big deal, and it has impacted the whole field of compressed sensing. These are the main papers that initiated this study. Let me also say what this is. With high probability, so I'm actually making these statements when G is picked generically, and I'm saying with high probability means that the probability of exact recovery goes to 1 exponentially with the number of measurements. So 1 minus e to the minus cm. I didn't write it down, but that's what we mean with high probability through this talk. Okay, so this is famous result. There exists another parallel, similar type of result for another type of structure, and that is a low-rank matrix. For low-rank matrices, we have this norm. It's called trace norm or nuclear norm or Schatten-1 norm, which is equal to the sum of the singular values of the matrix, and it behaves exactly like a 1 norm did for vectors. So here I have a matrix. The rank is R. R is much less than the dimension n. And if I were to solve this non-convex problem of finding the minimum rank matrix subject to the measurements, order of n times R observations are enough. And if I actually form the convex relaxation, which is this, it has been shown, in fact, this is from a paper by Candice and Plan in 2009, that order of nr observations are also enough for this problem to give you the same x0. And again, very striking, same order. Even though we went from a non-convex problem to a convex problem, order and R measurements are enough. And another thing to note is that n times R is on the order of degrees of freedom of a rank R matrix, where I mean by degrees of freedom, I mean how many parameters, for example, you need to describe the matrix. Okay, so these are two well-known results of this kind. And in this talk, we want to look at another kind of structure, which is simultaneous structure. So in many applications, I know more than one piece of information about my model. I know the model is simultaneously structured in more than one way. And one would hope that if I take into account all of these structures that I know at the same time, I should do better in terms of how many measurements I need for recovery. Because I've reduced the degrees of freedom. The object now, we have several structures at the same time. So for that, one problem to consider is the following convex relaxation. I want to consider regularizers. So these are some functions that we are going to identify, whose linear combination, when minimized, will recover x0, subject to the constraints. We are also going to allow extra information on this object modeled by a convex cone C. Another way to look at this problem, which may be more familiar to machine learning audience, is think of it that way. This is the, x is the unknown or the model I want to find. These are the measurements I have. And there's a loss function that penalizes how far I am from matching my measurements. So this is kind of a fitting error or loss. And then I have regularizers that try to encourage particular structures. And I have tau of them linearly combined, adding to each other, because I know tau things about this structure. So you can think of it like this. And what we are trying to do is we are basically trying to make a statement about sample complexity of such an estimator to recover the correct solution. An application of this, it comes up in signal processing, in particular in optics. And this is a classic problem called phase retrieval. So in this problem, you have a signal x0 that you make measurements of, and the measurements are linear, except that after you take this linear measurement of x0 with the vectors ai, you will lose the sign, or if it's a complex number, you will lose the phase of the measurement. So you have absolute value of that number given to you. So you have m measurements, but they're phaseless measurements. And the problem is now we still want to recover x0. How do we do this? It can be reformulated as follows. So this is not a linear constraint anymore, but we can linearize this by defining a new variable. I define a matrix that is a rank 1 matrix. It's the outer product of the signal x0. And then the measurements can be rewritten like this. AI transpose inner product with x equals these squared by just simply squaring both sides of this equation. And now I have an equation or measurements that are linear in this new object, which is a matrix. This matrix is rank 1. And it's positive semi-definite, and it has this linear constraints, which are these measurements. So this has been done in a recent paper by Candice and co-authors. And now what we are going to do is that in a lot of applications, we know the signal x0 we are trying to recover is also sparse. So what does that mean about the matrix X? It is rank 1 and sparse at the same time. So it's an application in which we have more than one structure for the same object. And well, one reason this comes up is that in optics, when you're measuring intensity, and that's why you can't measure the phase. Measuring phases is very, very hard. So it's been a big problem in signal processing for many decades. And there are different solutions. But OK, so what are our results? We are going to give a theoretical analysis of general simultaneous structures. And we are going to show the combined convex penalties has a fundamental limitation. Then we are going to specifically restrict ourselves to the case of sparse and low-rank matrices and show that if I write down a convex and a non-convex problem for recovery, unlike the cases we saw for sparse vectors and low-rank matrices, there is a large gap. So I need to define, I'll have one definition to make, and then one lemma and one theorem. So definition is this one. We are going to look at particular types of norms. OK, the time is very limited, so I'm going to go fast over this one. But we are going to basically look at regularizers that are norms. These norms have a certain property. And the property of the norm is called decomposable. Norm at a particular point x is decomposable if it has the following property. If there exists a subspace T, which acts like the support, and there exists a vector E, which acts like sign, such that all subgradients of the norm at point x can be written into these two pieces. So this is projection onto T, and this is projection onto orthogonal complement of the subspace T. Maybe it's best to see it in an example. So if I'm talking about, for example, sparse vectors like this point in 2 dimensions, this is the unit ball of the L1 norm. And at this point, which is the point 1, 0, the sign vector is going to be this unit vector of 1 and 0. For example, if I were at this point, it would be minus 1 and 0, so it captures the sign. And this subspace T is going to be this axis. T perp is going to be the orthogonal complement, which is this axis. And G is, for example, a subgradient of L1 norm at point x0. So the norm is not differentiable at that point. Therefore, I have a whole set of subgradients, which is this cone. G is one of those. And so this decomposability says G can be written as E plus projection of G onto T perp. And this projection has dual norm less than 1. In this case means infinity norm less than 1, means that the projection lies between -1 and 1 along this axis. So that's what decomposability means for L1 norm. But it holds for a bunch of other norms too. For example, L1-2 norm, other mixed norms, nuclear norm, and so on. Now, using that definition, we're going to have a family of such norms, tau of these norms. And I'm going to just denote the sign vector corresponding to every norm by EI, the support by TI. And most important object we need to define is the intersection of all the support spaces. T cap is the intersection of all the TIs. And projected signs are denoted, so sign vector projected onto T cap is denoted by this. I think this battery ran out. Oh, thank you. Yeah, so the projection of E onto T cap is denoted by this notation. And then these are some angle between the E cap and the EI. So what does that mean? So in this example, suppose this is X0. It has simultaneously 2 structures defined by, the first structure has this support space T1, and it has the sign vector E1 that lies in T1. The second one has this support space T2 and sign vector E2. X lies in the intersection of the 2 spaces, which is this line, which is T cap. And then the projected sign vectors are going to be these 2 projected onto the T cap. So the reason we are defining this is that in order to analyze the performance of such methods, we need to have a way to capture the geometry of each individual norm plus the relative geometry. How do they relate to each other? And so we are going to look at this optimization problem, minimizing summation of norms subject to linear equality measurements. And here lambda I are regularization parameters. And one result we can show just based on optimality conditions of this optimization problem is that if the number of measurements m is less than this bound, then the program will not recover X0 with very high probability. So recovery will fail with very high probability. Now this quantity depends on this function f used in the in the function here, it says you look at among all the subgradients, you look at the one with the smallest projection onto t cap. So this is not so informative, but let me actually specialize it with one more assumption. If I make the extra assumption that the inner product between all the projected signs are positive for all pairs I and j. And if you're interested in how we justify this, I can tell you later, but it's not a bad assumption, we can justify. With this assumption, our result actually simplifies to the following. If m is less than a constant times the minimum of the dimension of the ti's, so among all these t's, I take the one that has the smallest dimension. If m is less than that value, then recovery fails with very high probability. So that's actually the main point of our result, which is the bottleneck in recovery, a lower bound on how many measurements you need for it to even be able to recover the answer is going to depend on the minimum dimension of the t's, rather than one would have hoped it would depend on the dimension of the t cap, because that's where the x naught belongs, and that captures the real degrees of freedom of x naught. So we can also handle additional cone constraints that I didn't include in this result. But so that is a surprising thing. Our bottleneck is going to be the minimum of the ti's, not dimension of the intersection, as one would have hoped. And this is about the constants that appeared there, but we don't care now. If we actually specialize this result to the case of sparse and low rank matrices, we will see the gap clearly. So a matrix of size n by n, rank r, which is non-zero only on a k by k submatrix, has this many true degrees of freedom, true number of parameters to represent that matrix. If I solve the non-convex optimization problem like that, and here this means the number of non-zero columns, and this is the number of non-zero rows. I'm using the mixed norms to encourage the block structure, and this is rank. If we solve this problem, we need this many measurements to recover x naught. If I solve the convex relaxation, including a PSD constraint, I'm going to require order of n times r. So the gap between the two, this depends on ambient dimension. It's linear in n. This only is linear in k, and only depends logarithmically on n. Very large gap. So if we contrast this, for example, so there are more such results, and actually we can verify it numerically as well with experiments, but I'm out of time. Ask me later if you would like to know. But to summarize, we would like to have regularizers that would recover a simultaneously structured object. A most common thing to do is you take a convex combination of known penalties or norms that promote each of these structures and minimize those. However, surprisingly, such a program has a bad performance in the sense that it requires many more generic measurements than what you would expect based on degrees of freedom of the object. And contrast this with how cardinality and L1, how well L1 works compared to cardinality, and how well trace norm works compared to rank. There were no gaps in these recovery results, but simultaneous recovery has a big gap. And finally, so this is our result, but we have a lot of things to continue after this. Some of these are, for example, here I assumed Gaussian random measurements, but for example, in phase retrieval problem, measurements have these forms. So we need to extend the results to this more general case. We also would like to prove when we say recovery fails, it fails badly in the sense that the solution you find is at least certain distance away from the true solution. So you're not failing, meaning that you're very close to the true solution. Okay, I'm completely out of time, so I'm going to not talk about algorithms and other applications, but if you have questions, I'll be happy to describe more. Thank you.
We have time for a quick question or two from Maryam.
So is there any hope in the sense that maybe there's some other way of combining the triangles, let's say the sparse and the rank, other than by doing convex combinations in a way that you get in that?
Yeah, very good question. So that's a question we would like to address. It's not obvious. I mean, you would have to go back and see, can you, for example, define new atoms or unit objects that capture both structures at the same time? Basically, you would try to describe this intersection space from scratch and not thinking of it as intersection of this space and that space. Because if you do that, we showed all such combinations will fail. So is there another approach? In general, probably it's hard to answer, but in specific cases, one could approach them one by one and see if you can construct the correct norm in some sense.
Okay.
So
one last question.
question about special case of sparse matrix. If you have categorical variable and transform it to dummy numerical variable, so is this a special case of structure or not? Could be treatable as special structure or not?
I'm sorry, I didn't.
Let's say I have predictive modeling task. I have categorical variable.
So categorical.
So I transform categorical variable to number of category -1 dummy variables, which values are 0 and 1s, and 1 happens only once per number of categories. So,
so it's indicator function.
So it's a little bit sparse. It's not absolutely sparse, but a little bit sparse. So is this a special case when your technique could be applicable?
I'm not sure. So I'll talk to you afterwards in more detail. But approximately sparse signals have been also studied. Doesn't need to be exactly sparse. And all of these results we can say approximately structured. So for example, close to low rank or close to sparse. So.
Okay, let's thank the speaker.
Thanks.